Thank you everyone for joining. My name is Wilber Vrijburg, and I'll be discussing the accelerating of electrocatalyst synthesis and composition screening via spark ablation. Just a quick background about myself. In 2019, I completed my PhD in heterogeneous catalysis, so I come from a slightly different field, and this was at the Eindhoven University of Technology. And during this time, I studied nickel-based catalysts for CO2 hydrogenation. And since the beginning of 2020, so just before Corona, I joined Vsparticle as an application specialist. And my role here is really to interface between academic and industrial catalysis groups and Vsparticle, and then also explain and introduce Vsparticle's technology to groups, catalysis groups within the field. So as we all know, electrocatalysis is a rapidly growing field with a strong academic and industrial relevance. And one of the major driving forces in the last few years behind the surge of interest in electrocatalysis has been the need for us to mitigate climate change and transition towards clean, efficient, and sustainable energy sources with effective energy storage solutions. In addition, the electrification of our chemical industries has made the development of efficient electrocatalysts even more important. Now, there have been several recent studies that have demonstrated the wide-ranging applications in which electrocatalysts are employed, with some of the most relevant ones being CO2 valorization, water electrolysis, and fuel cell applications. However, and I think this is a big however, one of the biggest challenges that are being faced within electrocatalysis is the need to overcome the significant catch-up that it needs to play with respect to heterogeneous catalysis, because heterogeneous catalysis has seen incremental improvements over the last 150 years, and electrocatalysis really needs to catch up with respect to that field. So for this reason, there's also a need to screen a vast array of potential materials and material compositions to obtain novel electrocatalysts that are highly active, stable, cheap, and industrially scalable. So since the beginning already, we've been talking to researchers within the field of catalysis and electrocatalysis. And some of the feedback that we've been hearing from researchers within those fields include that they want to be able to develop synthesis methods that can allow their PhD students to focus on just the catalysis research and not on the synthesis of it. They would like to develop synthesis methods that can quickly and reliably prepare reference or model electrocatalysts. And lastly, and this one again is relevant to the significant catch-up that electrocatalysis needs to play, there is a desire to accelerate the discovery and optimization of new electrocatalytic compositions by screening their performance under industrially relevant conditions. So what I'm hoping that you're going to get out of this presentation is that you'll have a basic idea on what the technology that we use is based on, namely spark ablation, and understand how flexible this method is. I'd also like you to understand how our technology can simplify the preparation of model electrocatalysts, and that you understand how our technology can accelerate the discovery of novel electrocatalyst compositions to meet our future sustainability demands. So here's a quick outline on how the remainder of my presentation is going to unfold. To begin with, I'll discuss the VSP-G1 Nanoparticle Generator. This is really the core technology from which our entire product line is based on. After that, I'll discuss the accessories that can come with the Nanoparticle Generator, and then I'll illustrate how we can use it to prepare a single electrocatalyst. And in the end, I'll discuss the VSP-P1 nanostructure material printer, which is something that we use to then accelerate electrocatalytic screening by preparing these electrocatalysts in high throughput. First, the G1 Nanoparticle Generator. So our VSP-G1 Nanoparticle Generator uses spark ablation as the method to prepare its nanoparticles. So what I show you here are the ingredients that you need in order to be able to prepare these nanoparticles. To start with, you need to have conductive or semiconductive electrodes. You need an inert gas, so this can either be argon or nitrogen, which can then remove or take away the aerosol of nanoparticles that's produced. You need electricity, and the entire procedure runs at room temperature. So a high voltage is applied between these two electrodes, which leads to a spark being formed. And the spark then ablates or removes a small amount of material from the surface of these electrodes. And this vapor then sinters to form small atomic clusters. These atomic clusters can then form larger primary particles, and these primary particles can aggregate or agglomerate to form even larger particles. So overall, the input is electricity, electrodes, and an inert gas, and your output are pure ligand-free nanoparticles with a primary particle size of below 20 nanometers. We can form larger aggregates if we allow, well, I'll explain this a bit later. And the ablation rate in general is within the milligrams per hour range, but this really depends on which material you're using for your electrodes. So something that makes our technology unique, here on the left, we have our spark generator, we have the gas inlet on the left, we have our electrodes here in the middle, and we have our gas outlet on the right. And if we just zoom into the reactor head, we again see the electrodes here with the spark being formed between these two electrodes. We get the vapor of nanomaterial, and these then sinter to form larger particles. And what's unique about our technique is that we can vary the particle size by varying the residence time of the nanomaterial within this reactor head. So essentially, by varying the gas flow, we can vary the particle size. So higher gas flows generally produce smaller nanoparticles and vice versa. We're very flexible in the types of materials that we can prepare. It all depends on the electrode configuration that we use. On the left of this solid green line, I show you the types of materials that we can prepare using a single spark generator. If we have electrodes of the same material, we can form monometallic nanoparticles. We can form alloys by mixing and matching these electrodes, but the composition, the elemental composition of these nanoparticles will then vary between the two extremes of the individual electrodes. We can form more accurate alloys by pre-sintering or pre-alloying the electrodes, and then the composition of the nanoparticles that we form are equal to that of the electrodes that we start off with. On the right of the solid green line, I show you what happens if we have multiple spark generators. And here then it really depends on what the order or sequence configuration of these spark generators is, and that will then determine what your materials are. So if you have sequential deposition, you can really form layered materials. If you have your nanoparticle generators in series, you can form core shell type structures. And if you mix the two streams in parallel, you can again form some form of mixed alloy phase. Our spark generators are compatible with a wide range of materials. I show them here in green. Essentially, what you need are conductive or semiconductive elements, and they need to be pressed into or shaped into an electrode that's then compatible with our equipment. So if you have any questions about the types of materials that we're compatible with, feel free to get into contact with us and we can find out. Here I show you what an electrode looks like. So we have an end cap, which is part of the reactor head. And right at the end here, we have a click electrode, which just slots into the end cap. And essentially, it makes it very easy to vary or switch elements because they just click right into our reactor head. Now, after you've prepared your nanoparticles, you, of course, want to collect them in a certain way. And there are a number of different deposition methods that we use. The diffusion, filtration, and impaction methods are covered using the VSP-A series deposition accessories, and printing is covered using the VSP-P1 nanostructured material printer. And I'll go through all of these throughout the presentation. So first, I'd like to discuss the VSP accessories, and then I'll go on to a use case in which we prepare a single electrocatalyst. So first, the VSP-A series deposition accessories. Here on the left, we have our VSP-G1 nanoparticle generator, and if we combine them with these accessories, we can coat surfaces with nanoparticles. The fields in which we see these accessories being relevant are catalysis, sensor development, healthcare, energy, and filter development. And our accessories are numbered 1, 2, and 3, depending on if you're using diffusion, filtration, or impaction. And I'll go through them in this order. So first, the VSP-A1 Diffusion accessory. As you can see, this accessory just slots onto the end of our VSP-G1 nanoparticle generator. So we have our gas inlet here on the left, collecting our nanoparticles in the reactor head, and these are then deposited within the diffusion chamber on a substrate, which is held by a substrate holder. The diffusion accessory uses Brownian motion and the random motion of these particles to deposit the nanoparticles on substrates. The requirements are that these substrates are flat or two-dimensional, and they can have a maximum size of 1 by 1 centimeter. And by varying the deposition time, we can vary the surface coverage of these substrates between 1 to 10%. Applications in which we see this accessory being relevant include in situ TEM, in situ spectroscopy, electrocatalysis, but also just general materials research. And common substrates that have been used are TM grids, silicon wafers, and coated wafers. There are a couple of application examples I'd like to share just to illustrate what we can do with these accessories. The first one is an in situ TEM study. This was done in collaboration with Professor Günther Rupprechter of the TU Vienna in Austria. He's interested in studying model catalysts. Here on the right, I show you a HAD of STEM image of gold nanoparticles that were deposited on a TEM grid. It took 30 minutes to prepare this sample. Let's say the input material are just gold electrodes, and what you see in the HAD of STEM image are clean, surfactant-free, and crystalline gold nanoparticles. Similarly, we've worked with Professor Bert Weghauser here in the Netherlands. They've been very interested in studying nickel-based catalysts for hydrogenation reactions, and one of his former PhD students, Dr. Charlotte Vogt, used our equipment to prepare nickel nanoparticles on an in situ TM grid. It took 6 minutes to deposit these nanoparticles onto the chip. From the HAD of STEM image, you can see we have these bright spots, and using STEM eels, you see that it's a nickel core, and these nickel nanoparticles are completely free of any carbon contamination, which is then the unique part about preparing these nanoparticles in the gas phase. The third application that we have also comes from the group of Professor Bert Weghauser. This is an in situ Shiner study. Shiners is an advanced Raman spectroscopy based technique in which they can use gold nanoparticles encapsulated by silica to enhance the Raman signal of a reaction that's taking place on the surface of a model catalyst. So in this case, they studied nickel-based catalysts. They compared the preparation of these Shiners active materials using spark ablation, which is our technique, a colloidal approach, and an impregnation approach, the latter two being more conventional approaches within heterogeneous catalysis. And what they found in this study is that spark ablation was the only technique that yielded a Raman active catalyst at the end, and in doing so, it was able to be used for this Raman study. And this study was the first example in which a lower transition metal, so a first row transition metal, was used for a Shiners application. And the study came out at the beginning of last year. Next, we move on to the filtration accessory. Similar to all of our accessories, our filtration accessory just connects to the end of our VSP-A1 nanoparticle generator. So again, you have your gas inlet here on the left, collecting the nanoparticles, and then depositing them on a substrate that's in the sample holder. Our filtration accessory is compatible with substrates with a maximum diameter of 47 millimeters, and these are ideal for porous substrates. So it needs to be porous because you need to be able to pump the gas through the substrate. Applications include the preparation or electrocatalysis, photocatalysis, in situ spectroscopy, the preparation of just clean and unsupported nanoparticles, and the ground-up synthesis or production of electrocatalysts. And common substrates that have been used are just filter paper, carbon cloth, but also metallic felts and meshes. The last accessory that I'll discuss is the Impaction accessory. Again, this connects to the end of the VSP-A1 nanoparticle generator. We have our gas inlet on the left, collecting the nanoparticles. These are then accelerated through a nozzle, and this acceleration takes place because there's a vacuum pump downstream of the nozzle, and this then impacts the nanoparticles onto a substrate in the sample holder. Here, you can see it more clearly in the image. You have the acceleration of these nanoparticles through a nozzle, and they deposit onto a substrate. We can deposit metallic and oxidic materials. It all operates at room temperature and under a rough vacuum. And you can either use the Impaction accessory as a standalone accessory, but it's also implemented in one of our other products, namely the VSP-S1 size selector. And common substrates that have been used include silicon wafers and TM grids. So now I want to get to the first case example, and this is the preparation of a single electrocatalyst for the oxygen evolution reaction. So this work was done in collaboration with one of our industrial partners. They used the VSP-A1 Nanoparticle Generator and a VSP-A2 Filtration accessory. The Nanoparticle Generator was equipped with iridium electrodes. They could vary the voltage between 0.5 and 1.3 kilovolts, and the current between 1.0 and 10.4 milliamps. They used an inert gas, so either argon or nitrogen, and they could vary the flow between 1 and 15 liters per minute. And within the filtration accessory, they had their titanium felt as a substrate, and this is a 2 by 2 centimeter substrate that they used, and they varied the deposition time between a couple of minutes to a couple of hours. What was important here was their felt is square, and what we can do is we can just print a mask so that we can funnel these nanoparticles onto the felt directly. And this means that we're actually quite compatible with several different shapes and sizes of substrates that can be used in the filtration accessory. So one of the things that we can do quite quickly at VSP is we can determine these particle sizes of the nanoparticles in the aerosol stream. We did this for iridium for this industrial partner. This is done using a DMA, and this plot that I show you here, it's essentially it's a contour plot. Going from dark purple to light green, we see particle sizes between 4 to 18 nanometers. On the x-axis, we have the gas flow rate. So this goes from 1 liter per minute to about 15. And on the y-axis, we have the total power output. And what you can see is that we've got several different data points, which shows you that we can vary and tune the particle size between 4 and 18 nanometers just by varying the gas flow and the power output. So this also then helps the end user to quickly get going with preparing these materials. So these iridium nanoparticles were deposited on a titanium felt. We see that here on the left. This is what the material looks like directly after deposition. But for the oxygen evolution reaction, you need the oxidic phase of these iridium nanoparticles. So on the right, we show you the image of a calcined material. It was calcined in synthetic air at high temperatures, and it shows you that the material is quite stable. We got some SCM images. So here on the left, I show you the SCM image of the as deposited material. You can see these lightly fluffy particles here that are homogeneously distributed across the titanium felt. And these are then the iridium nanoparticles that have deposited across the titanium felt. On the right, we have the SCM image of the annealed or calcined sample. And what you can see is we've completely lost the fluffy material that was deposited. And this indicates that our iridium has indeed redistributed in the oxidic phase across the entire titanium felt. The performance of these materials was studied using cyclic photometry. Here I show you the CV plot of just the bare titanium felt. As we sweep from lower to higher voltages, we get some minor oxidation steps. And this is just the oxidation of titanium to titania. And as we sweep to lower voltages, we see minor reduction steps, which are the reduction of your titanium oxide to a titanium suboxide. If we then compare this to a CV plot of the material after iridium has been deposited, what we see here is that we get three characteristic reduction processes. The first one being the reduction of oxygen to water. The second one being the reduction of hydrogen ions to hydrogen atoms. And the third one being the reduction of hydrogen ions to hydrogen gas. And what this shows is that after depositing our iridium on the titanium felt, we were able to prepare a hydrogen evolution reaction electrocatalyst. And this confirms that we've indeed deposited metallic iridium on these felts, because those are active for the HER reaction. However, if we compare this to the material that was calcined, so again, here we have the CV plot, and now the plot in red is the calcined material. You see that all the reductive steps or the reduction steps are gone, and they've been replaced with a single oxidation step, which is attributed to the oxidation of water to form oxygen, which confirms that we've prepared an oxygen evolution reaction electrocatalyst. And this again confirms that we've prepared iridium oxide nanoparticles on these titanium felts after we've done the calcination step. So just a basic summary of this stage. The titanium felts can easily be modified with iridium using the VSP-G1 nanoparticle generator equipped with the VSP-A2 filtration accessory. After an oxidative treatment, we obtain iridium oxide nanoparticles on these titanium felts. And while the metallic and oxidic iridium on the titanium felts behaved as expected, we use this more as a way to show that we can readily and easily prepare reference materials for electrocatalytic studies. This same approach was also recently used, so this is at the back end of last year. It was recently used to prepare silver on carbon electrocatalysts, and this you can read this publication. It came out at the end of October. So knowing that we can prepare a single electrocatalyst now, the next step becomes, or the next challenge becomes, how can we employ Vsparticle's technology to accelerate the discovery and screening of new electrocatalysts to meet the demands of a sustainable chemical industry powered by renewable energy? And for this, we need the VSP-P1 nanostructured material printer. So this is what it looks like in our labs. I believe Ike has also shown a couple of videos earlier today. Here we have our VSP-G1 nanoparticle generator on the left. We have our gas inlet that then collects the nanoparticles, and these are then deposited within the VSP-P1 nanostructured material printer. There's a nozzle, and the substrate is then held on an XYZ stage. And then through this approach, we can deposit directly onto the substrate. The printer uses inertial impaction to accelerate these nanoparticles and then print them on various substrates. And some key parameters are that we can vary the deposition size, the spot size between 0.01 and 1 centimeter. The XYZ stage has an accuracy of 10 micrometers, which means we can really pattern these materials quite nicely. And we can vary the layer thickness on the substrate by simply varying the deposition time. Now, we're compatible with a wide range of substrates, but they should have a maximum size of 15 by 15 centimeters. And we've been able to print in MEMS devices, prepare surge chips, deposit on 6-inch wafers, as well as flexible polymers. Here I just show you two quick examples here. Pardon me. At the top, we have a copper oxide nanoporous film that was printed using our VSP-P1 nanostructured material printer. And at the bottom, we have a gold nanoporous film. So the next example that I want to show is how we can use the printer to prepare electrocatalysts in high throughput. This work was done in collaboration with Dr. Klaas-Jan Schouten, who is a part-time assistant professor at the University of Amsterdam. And until very recently, he was working full-time at Avantium. And Avantium is a Netherlands-based company based in Amsterdam, and they offer services and systems for catalysis research. But their core expertise really lies in doing high-throughput catalysis testing and screening. Now, Dr. Klaas-Jan Schouten was part of the Volta program, where they sought to convert CO2 to high-value chemicals via electrochemistry. And they really had a desire to develop high-throughput electrocatalyst screening methods. So in collaboration with them, they sought to prepare a high-throughput electrocatalytic screening cell. It was an 8x8 cell. So here on the left, we have a wafer. This wafer was then placed into a gasket, and this gasket is then placed into an electrochemical cell. And they can operate these electrodes either sequentially, so 1 by 1, or in semi-parallel, so 8x8. And they study the performance of the electrocatalyst using alkaline water splitting at industrially relevant screening conditions. So it was Vsparticle's job to then deposit the materials on the wafer. How this was done is we took their wafer and we placed it in the printer. The printer was equipped with two VSP-G1 nanoparticle generators. One of these had nickel electrodes. The other had iron electrodes, and what we could do is we could vary the elemental composition of the deposited material by varying the relative power output of the nanoparticle generator with nickel in it and the nanoparticle generator with iron in it. So in doing so, we could vary the nickel to iron ratio. We could also vary the layer thickness just by varying the deposition time that we used to get the nanoparticles onto each of these electrodes. And the test reaction that was used was the oxygen evolution reaction, and this was done at relatively high current densities. So here again we have the cell. The results that came out of it. So on the left here, I show you the cell potential and how this varied with different nickel content. And what we see in general here is that at lower nickel content, we get a lower over potential. So implying that we have a more efficient electrocatalyst for the OER reaction. On the right, I show you how the deposition time, so the layer thickness, influenced the cell potential. And what we see here is that there appears to be an optimal layer thickness, at which point we obtain the most efficient electrocatalyst for the OER reaction. If we superimpose these two plots on top of each other, so what we have here is the cell potential that if we go from light green to dark blue, we go to lower cell potential, so a more efficient electrocatalyst. And what we find here is that an ion-only catalyst with an optimal layer thickness was the most efficient electrocatalyst for this particular system. And this confirmed that we were able to then prepare electrocatalysts in high throughput and also study them in high throughput. So what I hope to have showcased here is that with the VSP-G1 nanoparticle generator and the VSP-A2 filtration accessory, we were able to prepare a single electrocatalyst quite quickly. And we can use the VSP-P1 nanostructured material printer to prepare electrocatalysts in high throughput. We have a number of webinars also for the other technology that we have, so feel free to take a look at them via our website. If you have any more interest, we have a number of these application notes also available on our website, so just go to vsparticle.com/applications. If you have any sales inquiries, please email us at sales@vsparticle.com. And if you want to have a demo request, so if you want to try out your own substrates for yourself, please visit our website at vsparticle.com/demo or email us at demo@vsparticle.com. Now I'm open to any questions.
Thanks.
Is everyone
Wilber.
still there?
Nice overview of the work that we are doing. Maybe a question from my side.
Yeah.
You didn't mention how quickly or how much time it took to synthesize the 8x8 different electrodes.
So this is indeed, this is in the plot. So maybe I can actually just share that again, just to make it a bit clearer. But essentially, it took up to, I think, 6 minutes per plot, per electrode. So you can see that in the, where are we? Here, in the deposition time. So if I just open it here, we go up to about 360 seconds as the maximum time needed to deposit the material on one of these electrodes.
Yeah. If I remember correctly, it took roughly maybe slightly more than an hour to synthesize all these different compositions.
Yeah.
And it's maybe good to mention that there was so we programmed the full printer, so the two G1s together with the printer. It was a full computer script. We just pressed the button and then all the dots were synthesized automatically. And after an hour, we just opened up the chamber and took the sample out. So there was no intermediate work done by a human.
Indeed, and this is I guess in general the thing with the printer. Once you've optimized it a bit, it's a matter of just putting your substrate in there, choosing your starting position, and then getting it going.
So coming back to what Massimo also mentioned, this is 64 different dots. For our process, we could also optimize it for 200,000 different dots. Then there will be quite some challenge to do high throughput analysis of those numbers, but from our point, there's no real bottleneck that stops us. Now we use two G1 sources, so two different elements. We can also have 6, maybe 10 different G1 sources. So we can mix an enormous amount of different materials together in the same manner as we did with this one. At the moment, so this is something that has been published. In the moment, we are also working with others. For example, Martin Kohle, that also joined the discussion before, who is working on high throughput experimentation. So if people are developing these tools, we are open to collaborate and to use our accelerated synthesis part to speed up the work. I see a question coming up from Julia.
Hi, yeah, this is Julia from TU Eindhoven. And my question is about the method that was used to deposit the iridium particles on the titanium felt. So I think this was the filtration method.
Yeah.
Yeah. Is it possible to know how much of the material, maybe by mass, was actually loaded onto the felt?
So yeah, it's a good question. It's also a very pragmatic question. So what we do initially is we also get an estimate on what the ablation rate is for the individual electrodes. You can always weigh your felt before and after. It's not necessarily the most accurate way of doing it, but I think in Eindhoven they have quite accurate analytical balances that can then also help with that. So that can give an estimate, but what also influences the amount of material that is actually deposited is how tight your felt is. So how tight the mesh is. So what you'll see is with a smaller mesh size, you'll be depositing more material on there because you have a more efficient deposition efficiency.
Okay, thank you.
Yeah, so coming back to the topic, at the moment, there's still some practical work to be done, but we are trying to, let's say, create a kind of digital twin of the process that should help you also in giving these answers upfront instead of needing to do all the analysis afterwards.